Hi everyone, and welcome back to Physics 2A. We're going to talk about temperature, kinetic theory, and gas laws today. So let's go ahead and get started. Now, the idea of temperature comes from the idea that there is some kind of heat transfer, and we'll talk about that in the next module more in depth. But heat transfer is maintained by temperature differences, and it is also the movement of heat energy from one place or material to another. Okay, so I've got some examples here. Say when you are heating up a pan to get ready to cook, okay, that's an idea of heat transfer. The flames going into that pan, okay, are coming into contact with that pan, heating the pan up. We've got heat from inside the earth, and that comes up through the earth, through the mantle, and it will come out as lava. And then we have heat from the sun, okay, and obviously this is not to scale. We are not that close to the sun, but we have heat transfer from the sun to earth. And again, we will talk about this in our next module more in depth, but just to kind of get you going with the idea of why we are looking at temperature. So temperature, it came from the concept of hot and cold, and that's by our perspective, okay? And what we have defined it as now is a measure, okay, with a thermometer. So whatever we measure with a thermometer, that is defined as temperature. And in temperature, we have some different scales. So here in the United States, we use degrees Fahrenheit, okay, to measure our temperatures typically, okay. And so I have this scale here from your textbook, and we can see the differences between these scales, okay. So, again, in the US, we typically use degrees Fahrenheit, and the freezing point of water in this scale is 32 degrees Fahrenheit, and the boiling point of water is 212 degrees Fahrenheit, okay? Now, a lot of other places in the world will use Celsius or degrees Celsius, and they define the freezing point of water as 0 degrees Celsius. So that is how 0 degrees was defined, was by what is the freezing point of water, okay? And the boiling point was defined as 100 degrees Celsius, okay? Okay, and the last temperature unit or scale we have here is called Kelvin, and it's denoted with just a K, so no degrees K, it's just Kelvin, okay? This is an SI unit, so our scientific unit, okay? It is the absolute temperature scale, and it's defined to have 0 Kelvin as the lowest possible temperature, okay? So you know that in Fahrenheit, we can get below 0 degrees Fahrenheit, right? We can get into the negative values. Same thing with Celsius, we can get into the negative values, but with Kelvin, 0 Kelvin is the lowest possible temperature, and this is called absolute zero, okay? At absolute zero, molecules stop moving, okay? And you'll look at that a bit more in your lab as well, okay? So, in Kelvin, the freezing point of water is 273.15 Kelvin, and the boiling point is 373.15 Kelvin. Okay, so notice the difference between Celsius and Kelvin. There is just an adding difference, right? Okay, and we'll talk about that right here. So we can convert between these temperature scales. Okay, the simplest one would be from Celsius to Kelvin or Kelvin to Celsius. Okay, So from Celsius to Kelvin, so if we're given Celsius, okay, as our temperature, we convert it in this way, okay? So our temperature in Kelvin will then be equal to our temperature in degrees Celsius, so what we were given, plus 273.15. Okay, and as you notice from the last one, our freezing point in Celsius was 0 degrees, right? But our freezing point in Kelvin was 273.15 Kelvin, okay? So that's the difference here, okay? And then to get to from Kelvin to Celsius, so we're given a temperature in Kelvin, we would do it in such a way. So really just rearranging this formula, okay? In this table 13.1 in your textbook, they also have Celsius to Fahrenheit, which maybe you guys have learned about, maybe not, and that's okay. But this is how you would do that. You also have Fahrenheit to Celsius, Fahrenheit to Kelvin, Kelvin to Fahrenheit. Okay, so you've got all these different variations in your table here. Okay, so let's go ahead and do an example when we have to use one of these conversions. Okay, so example 13.1 states room temperature is generally defined to be 25 degrees Celsius. Okay, and A asks what is room temperature in degrees Fahrenheit. So we're given in degrees Celsius, and we want to find the temperature in degrees Fahrenheit. So Celsius to Fahrenheit. Okay, that's going to be this first one here. Okay, so we have temperature in degrees Fahrenheit equals 9/5 times our temperature in degrees Celsius, which was given, plus 32. Okay, so this is our conversion. So we can go ahead and plug that in. It's a 5 times our temperature in Celsius, so 25 degrees C, plus 32. And so our temperature in degrees Fahrenheit then is 77 degrees Fahrenheit. Okay. Now it asks, what is that temperature in Kelvin? Okay, well, let's go back. We're given Celsius and we want to get to Kelvin. So we can use this equation right here. So our temperature in Kelvin is going to be equal to our temperature in degrees Celsius plus 273.15. Okay, so we can plug that in, 25 degrees Celsius plus 273.15, and we get 298.15 Kelvin. Okay, so hopefully this wasn't too difficult to follow. It's really just converting temperature. Okay, and now I want to mention the temperature ranges in the universe. Okay, so one thing that we can note, is really the first thing, is human beings have a range of temperatures that we can withstand, and that is 24 degrees Celsius to 44 degrees Celsius, or 75 degrees Fahrenheit to 111 degrees Fahrenheit. Obviously, that'd be running a fever. And our average temperature is 37 degrees C, or, whoops, that should be an F, degrees F, or 98.6 degrees Fahrenheit. Okay, and that's typically what our body tends to run at. okay? And we see this temperature scale, and it might be kind of hard to read, but it is in your textbook, okay? And just to show you that big range that we have. So we're not just looking at things that are relatively cool, but we're looking at stuff that's very hot as well. Okay, so we've got liquid helium, nitrogen. We go to Antarctica. Okay, we've got freezing water, where water boils. We have solar surface, the interior of the sun, solar corona, solar interior, and so forth. Okay, so we've got temperature rising in this direction. And we can also go into this opposite direction, okay, where it gets very, very cold. Now, obviously, we don't have very many things that are very cold. And that's because as you get to 0 Kelvin, okay, that's 0 Kelvin, not okay, 0 Kelvin, molecular motion stops, okay, like I mentioned earlier, that's at absolute 0. Okay, all of the molecular motion is stopped. Now, that is very difficult to achieve, okay, because there's always some kind of heat or some kind of temperature to molecules. They don't want to stop moving. So it's very, very hard to achieve absolute 0. Okay. Okay. So moving on to thermal equilibrium. Okay. So when we place two systems in contact with each other, heat will flow from the hotter object to the cooler one until they reach the same temperature, and that is called thermal equilibrium. Okay. So again, heat flows, and I believe we'll probably talk about that more in our next module, but heat will flow from the hotter object to the cooler object, okay? And there is a law of thermodynamics called the zeroth law, and it states if two systems, A and B, are in thermal equilibrium with each other, and B is also in thermal equilibrium with a third system, C, then A must be in thermal equilibrium with C as well. So if A and B are in equilibrium, and then B and C are in equilibrium, that means that A and C are also in equilibrium, okay, which makes sense. Okay, there's a lot of wording here, but it makes sense, okay? Now we need to talk about thermal expansion, and you may have noticed this in your everyday life. This happens in the summer versus the winter especially, okay? One thing you may note or notice is that when you are shutting doors, sometimes they will have a harder time shutting completely or kind of like sealing together. Or what else? It might be super easy to open a door, and that's because of this thermal expansion. In the heat, things tend to expand. In cooler areas, it'll tend to contract, okay? So we are looking at this thermal expansion of objects, okay? And this is, again, the change in size or volume of a given mass with some temperature, okay? And we do have an equation for that, and that is going to be the change in length is equal to a coefficient of linear expansion, which varies with temp, times the length, L, times the change in the temperature. Okay, so this is thermal expansion in one dimension. Okay, so we'll see in a couple of slides thermal expansion in 2 and 3 dimensions. Okay, so I'm going to go ahead and let off here, and then we'll start in our next video.